Hello everyone, nice to see you. So today we have our last lecture and we will focus on such topics as photodiodes and LEDs. So just short recall, last lecture we discussed solar cells. We will probably during this lecture recall something about our previous discussion because it definitely has quite a lot of overlaps with photodiodes, but definitely PN junctions and other rectifying junctions can be used not only in this photovoltaic mode, but when they act as generator of electric power, but also in photodiode mode when we apply some reverse bias. So let us see some current voltage characteristics which can simulate it for different light intensities. So that's what we typically consider for solar cells. And as you see, we have this fourth quadrant here. So we can easily determine some main photoelectric parameters from such JV curves. So any suggestions which parameters we can get from these illuminated JV curves? Hey. Okay, so short circuit current. Okay, this is our short circuit current. Also, you mentioned about voltage, yes? So obviously, this will be like probably let's write it in our units like VOC. What about fill factor? How do we get it?
You draw a rectangle.
Rectangle. You can draw many rectangles. You need to draw the rectangle, and the rectangle. How do you? It should be rectangle with the largest area, which can fit into this current voltage characteristic. How? What is the approach? How we get this maximum current and voltage?
For the maximum rectangle, you look for the area, like.
Sure, but you don't know. You can. I mean, you will not draw 100 of rectangulars and check which one will be with the largest area. There is a straightforward approach how you can determine maximum voltage and maximum current.
Then you find the maximum power.
Oh, so how do we do that? We need to plot one figure where will be here voltage and here will be product of current, this current which we measure, times voltage. So that is electrical power which is delivered by solar cell to the external electric circuit, to the load resistor. That will be some curve with maximum, and at this maximum output power we will get maximum voltage. This will be P maximum, and P maximum is equal to V maximum times I maximum. So from here, I maximum is equal to P maximum divided by V maximum. So with this simple approach, we determine where are this maximum V maximum here, and here will be I maximum. So in this case, that will be the rectangular which we consider, and the ratio of this maximum power I maximum times V maximum divided by I short circuit times V open circuit, that should be equal to our fill factor.
Can I ask, this problem we have plotted power against voltage, PV.
Yes.
We have the curve having this way parabolic, like the curve is upside down.
I mean, that's because you took negative current.
Yeah, when we...
So you need, but power cannot be negative, so you just means that you by definition take absolute value of this, so it will be flipped over, it will be, you cannot have negative power, it's not fighting against thermodynamics. So that's, since you have negative current in terms of, because photocurrent is in the same direction as reverse current, we discussed this previous time. It's negative because reverse current is negative, but when we consider power cannot be negative, so we take absolute value. So that's about solar cell parameters, and let me again remind you, because you may forget, so this is important. Hello, we were missing you. So this is efficiency of a solar cell, or probably we can denote it as PCE, photo conversion efficiency, and that is equal to these three main photoelectric parameters, VOC times short circuit current times fill factor, divided by P input. P input is the total energy of sunlight which hits the surface of the solar cell. So you already know all these things, we just recall it from previous discussion, but we need to highlight that this is this photovoltaic mode of p-n junction operation. And there is one more possibility. So we can go for so-called photodiode mode. So what's the difference? With photodiode mode, we obviously do not use our p-n junction as electric power generator, because here we apply some reverse bias. So we attach our p-n junction to some power supply with polarity which provides reverse bias, and obviously we provide some electric energy from outside, from external power supply, to our diode in order to push it in reverse bias, what help us to increase internal electric field, make the width of the depletion region wider, and that actually makes more efficient charge carrier, photo-generated charge carrier collection. So current voltage characteristic, how they look, it's actually quite flat. You can see for different light intensities, it just with very small slope, because efficiency of charge carrier photo-generated charge carrier collections increases slightly with reverse bias, but even at zero bias for good devices, we already collect most of the charge carriers. But there is still some slope, means we improve a little bit this collection. And why do we need this? So photodiodes, these are usually small area devices. So here are some examples which are commercially available. You see they can be quite tiny, from like few millimeters square to maybe like 1 centimeter square. That's usually like maximum area for photodiodes. Obviously they are not designed to collect a lot of light and convert it to useful some electric current which can run some devices or charge batteries. Their purpose is collect very weak signals and very fast signals. And in both cases, when they are like signals, like light signals are weak and fast, they want to convert these signals into measurable electrical signal, electrical current. So that's why we apply reverse bias, in order to be sure that we have the most optimal conditions for collection of photogenerated charge carriers. So we cannot allow to lose them because we don't have many photons. These signals can be very weak, low in intensity, and that's why we need to collect as many photogenerated charge carriers as possible in order to get some decent signal, which will be higher than the noise level. And noise level will be determined by this. If we come back here, so you see it's like dark current, which always present at reverse bias. So this current will mostly determine the threshold level for light intensity, which our devices like photodiodes still can detect. And also, as I mentioned, there is another important feature, is so-called time response of these photodiodes, because signals may be not only weak in intensity, they can be very fast changing. So if signal is changing very fast, in order to detect the proper shape of this signal over time resolution, we need to have a device which can very swiftly change photocurrent upon excitation of this very weak and fast optical signal, and represent us with measurable electrical current, like this photocurrent at reverse bias, which will be able to follow very fast optical signal. So that's why it is important for photodiodes to have high so-called detectivity, that it can detect low optical signals, and a high time response, so it can respond to different signals without modifying them because of lagging behind the signal, when the photocurrent is lagging behind the signal. So these are some key parameters, but obviously there are more, and we will discuss them in more detail, so you know what should be specifically of your interest when you deal, probably some of you design photodiodes in your research, or obviously in your future research. That's a big chance that you will somehow overlap with photodiodes in the lab for measuring this or that optical signal. So you need to know the parameters. So why do we care about photodetectors? That's quite wide range of possible applications, starting from some automation, when we have like sensors, like position sensors, like motion sensors, medical applications, when we have inspection of human tissues which are transparent for near IR spectral range, imaging, CCD cameras in our photo cameras, in some optical systems which are designed for like night vision or something like that. It's just all using CCD cameras with different resolution, different number of photodetectors per inch, and that allows to project with some lens the image on such sensor, and get the distribution of the signal all over the area of the detector with many pixels, and that's how we get high quality images. Also spectrometers, we can check. Yeah, probably you can make it a bit higher temperature somehow, it's a bit cold here. Spectrometers for analysis of optical properties of devices. And another important aspect of photodiodes application is optical communication. So nowadays, all these high bandpass internet connection networks, they are using optical fiber, and there you have fast LEDs and fast photodetectors which work in IR region, because usually this the wavelength is something like about 1.5 micrometers for best transparency in this optical fiber medium, and they're very widely photodetectors and LEDs, semiconductor LEDs are used. So there are three types of photodetectors. So first one is photoresistor. That's probably the most simple one. We just have active layer, which is some active semiconductor, and two contacts to this layer. So usually it's intrinsic semiconductor with high electrical resistance. So when it's in the dark, the resistance is very large and current is small. But when we shine with some light, we increase the conductivity significantly because of photogenerated charge carriers. So that's how it works. Another is photodiode, which is actually the same solar cell, because every solar cell can work in photodiode regime. Just a question if it will be the best photodiode, but it can work as a photodiode. So it's designed for different purposes to operate in photovoltaic mode, but it can always operate as a photodiode. And obviously every photodiode as a PN junction can operate as a solar cell in photovoltaic mode, but obviously the parameters, like photovoltaic parameters, will be quite low. And also there is a phototransistor option when we have a combination of this photoresistor with photoactive material here in between two contacts, which now are called source and drain. This all deposited on the electric layer, and here we have some heavily doped silicon or just metal, which serve as a gate electrode. So why we need this? We can modulate conductivity, like background, like in the dark, conductivity of this semiconductor layer here by gate potential. So we can push up and down the Fermi energy in this system, and because of external electric field, which can be quite strong since the electric is thin. So we can improve noise characteristics, so we can increase resistance of this active layer as it would be without any gate electrode, and that could be a good option to have this possibility to modulate characteristics of this photodetector. So our goal is photodiodes, because it's directly related to all our previous discussions and lectures, since we know a lot already about PN junctions, solar cells based on PN junctions, and of course we will consider photodiodes. So here in particular we have this so-called metal in semiconductor metal, or PIN structure. It's not PN junction, and we will show it here. So there could be two types of photodiodes. First, it can be based on a traditional, for us already, PN junction configuration. So that's this first figure. Then we apply some reverse bias. We make this width of the depletion layer as wide as possible. We know that there we will have large internal electric field, and any charge carriers which are generated here with photon energy larger than the band gap of the semiconductor material, they will be efficiently, this created photo-generated electron hole pairs will be efficiently separated by this strong electric field and contribute to photocurrent. So another option is if we want to have this highly resistive region, which is depletion region with strong electric field, so we can make engineer the device in that way that we by definition have this region almost everywhere. So that is the case for this PIN photodiode. So in this case you have highly doped P and N regions which occupy small part of this photodiode, and major part of the photodiode consists of intrinsic semiconductor with high resistance. So in that case, when we apply external bias, we create electric field, like strong electric field in all this area of intrinsic semiconductor, and that means in a wide range of this thickness of intrinsic layer, which can be much thicker than the depletion layer of a PN junction, we have efficient separation of photodiodes. So we can apply large biases and get efficient extraction of charge carriers. So for photodiode characteristics, that's really nice. For solar cell operation, that if you have really huge thickness of this intrinsic layer, which could work for photodiode and can be beneficial because it will absorb more photons, you need to extract these charge carriers, so these holes and electrons should be extracted. Obviously, we don't have ideal situation. Real life brings problems in terms of recombination losses and extraction efficiency, and that's why we need to apply large external bias. So with large external bias, we can improve this extraction. So we create conditions when most of photogenerated charge carriers will be extracted. However, if we operate it as a solar cell, we don't apply bias. Doesn't make sense. We want to get bias and current out from this device. So in that case, electric field will be very low. It will be defined at short circuit condition only by work difference between P and N regions. And with such low electric field, without external bias, it will be quite challenging to extract these guys, so they may recombine on the way. And performance of such optimized photodiode will be not great as a solar cell. But as a photodiode at large reverse bias, it will work very good. So that is just both can work as photodiode and solar cell, but taking into account some features of device engineering which are fine-tuned for these purposes of their application, they of course will work better as photodiode or solar cell. Cannot both be like of top performance, like one device cannot be of top performance photodiode and solar cell. So what do we need to know about photodiodes? First, it's good to know how we generate charge carriers inside. So for that purpose, when we have device architecture, let's say like these two here, these are also analog of metal intrinsic semiconductor metal structure with cadmium telluride and mercury indium telluride photosensitive semi-active layers. So we can calculate optical field distribution in such devices. When we have this geometry, by applying transfer matrix simulation, we can calculate how electric field, like optical field, which means electromagnetic field, will be distributed in terms of intensity within the active layer. If we know intensity as a function of position x within active layer, we can calculate generation profile. So because we know optical properties of all these layers, of course, absorption coefficient, we can calculate generation profile. So that's actually what's shown here in these two three-dimensional plots. We have generation rate. So what is generation rate? Can you remind me, please?
The rate at which electrons, mobile charges are generated in the
Okay, so it's per what?
unit key.
Per unit volume, per unit time. Yeah, so actually you can see these units here. And we have it as a function of wavelengths. You see, go from 400 to 800, and here is why the wavelength range, because it's narrow bandgap material from like 400 to 1600. And at each wavelength, within this photosensitivity region, we can predict position distribution of this photo generation rate. So you see that for instance, for this cadmium telluride, most of photo-generated charge carriers are created somewhere close to the surface, and not much is going on in the volume, while here, because of interference effects in this mercury indium telluride, it's kind of a bit more transparent than cadmium telluride, less absorbing. So we have kind of distributed generation rate within the active layer. And then obviously if we care about one wavelength, so we deal with one wavelength. If we care about all wavelengths, like whole spectrum, then we can integrate it and get this generation rate as a function of position x only, because we already integrated for all wavelengths. So that is the question related to photo generation, which obviously also matters for solar cells. So for both are important parameters, we need to know how much we generate and where exactly within the active layer we generate charge carriers. So now let us focus on photodiode main characteristics. So obviously that is current voltage characteristic. So this first figure A. We care for photodiodes specifically in this part for reverse bias, because they should operate at reverse bias. So we want to know what is the dark current for this photodiode at reverse bias. And the smaller this dark current is, the better it will be, because this dark current will establish some background signal, which will be the limit in terms of detectivity, like in terms of sensitivity of our photodiode. So obviously we want to keep it as small as possible. That could be achieved by increasing thickness. For instance, how it's shown here, we have thin and thick active layer, and you see that for thick active layer we have smaller current. But it can also change by interfaces, like modification of interfaces, preventing some injection into this active layer at reverse bias, and so on. It's quite a challenging task, but that's very important for photodiodes. So next photodiode characteristic is external quantum efficiency. Here it overlaps with solar cell also, because it actually shows us in which spectral range it will be photosensitive. For instance, so we here have this external quantum efficiency as a function of wavelengths. So we see that it's photosensitive from 400 up to somewhere 1000 nanometers. So what is defined? What defines this long wavelength range, where until which is photosensitive? It's obviously the band gap of this active layer. So if the band gap is already narrow band gap, it actually can create photogenerated charge carriers with longer wavelengths up to this threshold when photon energy is not larger anymore than the band gap. How we determine external quantum efficiency? We were talking a little bit about internal quantum efficiency for solar cells, but that's more like from fundamental point of view, because what we can really measure is external quantum efficiency, and we determine it in the same manner for photodiodes and solar cells. So we have total number of electrons which create external photocurrent. So for that purpose we have photocurrent divided by elementary charge, and that amount of that amount of electrons which create photocurrent, we divide by amount of photons at given wavelengths which hit the solar cell. So that is light intensity divided by h nu at monochromatic illumination. So that's definition of EQE. So we can also consider it as this photocurrent as this integral. So it's integral from 0 to L all along the active layer thickness for generation rate, position distribution within the active layer at given wavelengths times this eta is the extraction efficiency. How good at given condition, at given external bias, we can efficiently extract photogenerated charge carriers. It depends on position where charge carriers are generated. It depends on bias, because it defines the strength of electric field inside this device. Also depends on mobility of charge carriers and their recombination lifetime. So I mentioned that extraction depends on the efficiency of charge carrier. Photogenerated charge carrier extraction depends on external bias, and that means that EQE, external quantum efficiency, also depends on external bias. So here I show you one example for simulated EQE spectra for this. This is some cadmium telluride photodiode, and this black solid line here gives us some ideal condition when we extract all photogenerated charge carriers. And then we have already some more realistic cases when we have recombination losses and issues with extraction of charge carriers. And that's how EQE spectra is changing with increase of bias. We start from minus 0.1 volt, and you see that it increases up to this 10 volts, so minus 10 volts. Even at minus 10 volts, we still see some gap between total extraction of charge carriers and what we're supposed to get in reality. So we still have some recombination losses of these charge carriers, but the difference is much smaller than what we have here when we apply very small reverse bias. So that is EQE. It shows us how efficient our conversion of one photon to one charge carrier, which is collected already by electrons. So it shows, it includes both generation of charge carriers and efficiency of their extraction. Next parameter, which is very important, is responsivity, and that is already photodiode parameter. Usually for solar cells, people do not consider it. So responsivity is shown here on this side of the second plot B. Actually, these curves. It is related to external quantum efficiency with quite straightforward and simple equation. And what it gives us, it's measured in amperes per watt. So it literally tells us at given wavelengths, let's say we pick up some wavelengths of, I don't know, 900 nanometers, how much of what a photocurrent will be measured with such diode at 1 watt power of monochromatic illumination hitting this photodiode and at the wavelengths 900 nanometers or any other wavelengths which you pick up within the spectral range of spectral range of photosensitivity of this solar cell. So obviously it cannot be wider than the EQE spectra because we calculated from EQE, but it tells us in terms of electric current how much we will get when we shine on this photodiode with monochromatic light of given wavelengths and some given power. So that is used for calibration of photodiodes, and once you have such spectral distribution of this responsivity and some unknown monochromatic light source, like some lasers, you can use this photodiode, shine with this laser on photodiode. You know wavelengths, so you pick up the wavelengths of this photodiode. You check what will be the responsivity. You measure photocurrent. You know wavelengths, you know photocurrent, which is experimentally measured. So you check responsivity for this photodiode at given wavelengths, and that's how you can easily determine the power of this monochromatic light beam. So that is the main purpose for some calibration of signals.
Why is it that the responsivity is not associated with time? Because sometimes how responsive the solar cells are should be like associated with the time we shine the.
Oh no, I mean you mean that you heat up the solar cell and over time it reduces its photoelectric parameters?
How it responds to.
Oh, we will definitely discuss on next slide time response. Yeah, so that matters, but we assume that this is at steady state conditions. So that's the best what you can get. Of course, if your signal is so fast that your diode cannot follow this signal, then it will not work in the same way with the same responsivity. But when you provide responsivity, you also provide in like data sheet for photodiodes the so-called 3 decibel cutoff frequency. That means until which frequency this photodiode can be operated, and that the manufacturer ensures you that this photodiode will possess this responsivity characteristics up to that frequency. Like if you go to higher frequency, then of course that's not what you should expect. So that is what we measure. But in photodiodes, it also matters on which background we measure the signal. So it's good to get a large photocurrent, but if this large photocurrent is on the background of large reverse bias, this photodiode is not going to be a good device. For that purpose, we have this characteristic as detectivity. So here is the plot, detectivity measured in joules. So it actually tells us what should be the minimum intensity of optical signal, so we can detect it on the noise level, on the background of this noise level. And obviously we want to get higher responsivity, so we will get higher photocurrent at given conditions. But also we have here in the denominator the dark current, reverse current at given bias. Keep in mind that both depend on bias, on reverse bias. That ratio, so we want to, our good photodiode should possess high responsivity and small reverse current. That is the rule if you want to have a good photodiode. Now we can take a look how these parameters depend on bias. I have already shown you EQE as a function of bias in previous slide. And EQE obviously increases, so that is true for responsivity. So you see responsivity also increases with reverse bias. However, you may notice here that detectivity actually drops with increase of reverse bias. And why it happens? Because reverse current increases faster than responsivity with reverse bias. So what we want to have ideally for detectivity also increase at least up to some biases when then it saturates. Or we want to have it flat, so it would be also ideal situation. However, in reality, even for quite good photodiodes, we see such slight reduction of detectivity with increase of reverse bias. So we always need to remember that detectivity is a compromise between responsivity and dark current. So that's not the only parameters for photodiodes. As you notice already, it has actually way more parameters than main parameters than solar cells. We have only kind of 3 main photovoltaic parameters. Photodiode parameters are much broader. So next one, which is important, is so-called linear dynamic range. So it is important, since we use photodiodes for calibrating, for measuring light intensities, we want to have linearity of its light intensity dependence in as wide spectral range, so not spectral but intensity range as possible. And you may notice that in cameras you also have, like photo cameras, you have this parameter linear dynamic range. It actually tells you how realistically it can show you image where you have regions with very dark and very bright areas. So you don't go to kind of saturation in bright and still see something in dark. So you have this gradient with details which you can still distinguish in bright area and dark area. So for instance, when you have some background with some sunny sky and somewhere in the shade some people. So the fact that you can see properly the sky and people in the shade means that your camera possesses this wide linear dynamic range, and your detectors are of high quality, so it means you paid quite a lot for your camera, because that is not so easy to achieve for CCD sensors. And how we determine it? So we consider maximum light intensity, where it still remains linear, and minimum light intensity, where it still remains minimum. So here you see many orders of magnitude difference in light intensities, and the ratio between these upper and lower light intensities as decimal logarithm gives us linear dynamic range. So we obviously want to have it as large as possible. So now we come to this time response, and it's defined here in these two plots. So first, it's how photocurrent of photodiode depends on fast changing signal. So here we have on, here we have off. So on, off, so repeatedly we have this turn on and off of a light signal, and you see that at 20 kilohertz, this given photodiode, it's some organic photodiode, which I gave an example from our recent paper, it works quite well. So it repeats the shape, or the square shape of the optical signal, because you clearly can see when it's turned on, it goes to saturation here. So it means that photodiode responses adequately fast to this signal, and then quickly turns off. However, if we increase frequency up to 200 kilohertz, which is like one order of magnitude higher, this shape already doesn't look so good. It should be something like this. Actually, even not like this. It should be something like this, and that should go down and saturate here and again go up. But it doesn't. So you clearly see that photodiode already cannot follow this fast optical signal. The maximum photocurrent which we measure already is lower than this saturation level you see here. So the difference between them, which provides us with reduction of this photocurrent by 3 decibel, is so the frequency at which we have reduction of this maximum photocurrent by 3 decibel, that is actually so-called 3 decibel cutoff frequency, and that's how we determine it. We plot this normalized response. It's actually also decimal logarithm of the ratio between these two amplitude, saturated and actual amplitude, and we see that it's saturated, it's flat, it doesn't change, means in this region at low frequencies our photodiode works completely fine, it can follow the signal, and then it starts to kind of deviate from this saturation. And this moment when it crosses this minus 3 decibel, we consider as cutoff frequency. So what defines cutoff frequency? So this is our cutoff frequency. It is defined by transit frequency limit and RC frequency limit. And you see that we have like 1 over, means that when we have these two, the resultant cutoff frequency will be smaller than any of these transit or RC frequency limits. So what does it mean transfer frequency limit? It is literally associated with the time which is required for charge carrier to go through the active layer, to drift through the active layer and be collected. So obviously there is some distance, there is some drift speed, it takes time to move from one edge to this active layer to another. So that will be a function of mobility of charge carriers, of electric bias which is applied to the photodiode, which defines together with thickness L, defines the strength of the internal electric field. And RC, that is like RC constant, which you learned starting from general physics, electricity. If you have capacitor and resistor, which we do have, you remember we discussed this equivalent circuit of a p-n junction. We have a capacitor in parallel to a resistor. It takes some time to discharge capacitor through a resistor, and the larger capacitor and the larger resistor, obviously the larger it will take to discharge it. So this time RC time constant, which is like this guy, it will define how fast we can operate this photodiode. So it's determined by barrier capacitance of the junction, p-n junction, and also internal series resistance and external load resistance which we attach to this photodiode. So in particular, we calculated for this organic photodiode, you can see that the actual 3 decibel cutoff frequency coincides quite well with the transport frequency limit. RC frequency limit is at significantly higher frequency. So RC constant is not a problem for this device. That is actually the issue which limits the time response is our transport in the active layer. So these are pretty much all most important parameters. There are more, but these are the key photodiode characteristics which you need to know and understand. So now let us switch to LEDs. So far, solar cells and photodiodes, we shine light and extract charge carriers. But if this process is fundamentally possible, there should be a possibility to inject charge carriers, apply external bias, inject charge carriers in the active layer, as shown in this figure. They will meet, and there is a chance that they will recombine radiatively. So you remember during our probably second lecture, we in details discussed this radiative recombination in solar cells. So we quantitatively analyzed it. It doesn't mean that they will recombine radiatively. So that's what we should create conditions for in this device. So we need to definitely use very high quality, like emissive semiconductor layer without traps, because this trap assisted recombination is not radiative recombination. We need to band recombination. So we need literally to organize conditions when these injected charge carriers from electrodes meet each other and recombine radiatively, and then it will result in some light going out from this area, which we will observe either with eyes or with some detectors, depends what the spectral range, and that will be defined by the band gap of this active layer. This is similar, like most common photodiode, LED characteristic device architecture for so-called organic and also perovskite LEDs, where we have PIN structures. And what we need to get a good LED? So first of all, we need to inject efficiently charge carriers in active layer. Second, we need to organize radiative recombination. So again, no impurities, defects, and so on. So it should be band-to-band recombination, the most get out most of what is possible. And besides that, we need also to extract light quite efficiently, because let's say if you generate photons here in this active organic layer, it can go in different directions, it can refract and reflect from different interfaces, and what we really care is this, which actually goes from the front surface of the photodiode. All these photons which go, which are like undergo total reflection, and they go out at the edges, they do not count because our observer is here. So, how spectral distribution of LED looks like? So that is the image. We see some device on a glass substrate. We run some current through this device, and because of this electroluminescence, we see some light coming out. So if you put a spectrophotometer next to such LED, you will see some electroluminescence spectrum. Electroluminescence means we inject charge carriers because of applying electrical field. They recombine radiatively, and we get this electroluminescence signal. And that will be some spectral distribution with maximum corresponding to the band gap of this material. So it's not monochromatic light source, it's not a laser, but it's relatively narrow spectral distribution because it is peaked at the position of the band gap. So if you want to change the spectral distribution, you use different material with different band gap, and you could see something like this. You could see at different wavelengths these peaks, which will correspond from different materials. So of course you can combine them together, so you will get some distribution, spectral distribution. You can also use wide bandgap materials which emit in blue or UV spectrum. Then you will excite some luminophore, which will absorb and re-emit it in a broad wide spectrum. So that's how you can manipulate with this spectral distribution of light which we get out from LEDs. But if we have pristine material, just some active layer of one material, that will be defined by this maximum position will be defined by the position by the band gap. So with all these characteristics, we can introduce one of the key parameters for LEDs is quantum efficiency for electroluminescence. So we consider total number of photons emitted in forward direction, means in from this front surface of the LED to the number of electrons which are injected in our device. So obviously for that purpose we need two things. We need maximum outcome via radiative recombination, so all other recombination mechanisms should be minimized, and which are non-radiative. And second, we need to extract this generated light because of radiative recombination in the most efficient way in order to get it out from the front surface within some angle, like solid angle. So besides pure device characteristics, what really matters for LEDs is our perception of light, what LEDs, because that's either for illumination inside some rooms, or for OLEDs are used quite widely for screens, like this in particular. This screen is OLED screen. I don't know how long it will last, probably will degrade quite soon. But the quality when it's new is very good. so can compete with a lot of other technologies. And obviously we want to get a proper color. So we depends on which band gap material we use, we will get some spectral distribution. We need to know how this will look in terms of our perception of color. So according to the biology of human eye, there are two types of cells, like rods, which detect light intensity and show us like bright and dark sense, and cones, which are responsible for color perception, blue, green, and red. So here you can see on this plot so-called standard observer color matching functions. And this is the first step in order to understand how we will perceive, how our human eye will perceive the color of LED. So what we need to do? We need to multiply these functions for like x, y, and z prime. We need to multiply it with spectral distribution, like irradiance spectra, in watts per meter square per nanometer, which is illuminated by our LED. So we multiply each of these curves, three curves, with our spectral distribution of irradiance, and we get new three curves, like products of these. Then we need to integrate them. So these are our irradiance spectrum. These are these color perception functions, and we get so-called x, y, z color space parameters by integrating these products of these three this irradiance and three functions x, y, and z, like small x, y, and z, within the visible spectral range. So we integrate from 380 to like something around 790 nanometers. So then we get this x, y, z color space, and we can make next step now, get color coordinates. So color coordinates, here are equations for color coordinates, and taking into account that for color coordinates the sum of all color coordinates gives us unity, means we need only two color coordinates, because the third one we can easily determine. So that means that with determining, let's say, these x and y color coordinates, in the so-called chromaticity diagram, where we have this y and x color coordinates, we can determine, after all these manipulations, what will be the color of this particular irradiance spectra, which LED provides. So with known color coordinates, we can define some spot on this chromaticity diagram and determine the expected color from this LED. So a little bit more about this chromaticity diagram. This color spectrum locus, that is perimeter of this diagram. If we go all over the perimeter here, we see that actually points at this perimeter correspond to the color of pure wavelengths in the visible range from 780, from monochromatic light at 780 up to 380 nanometers. So this is color what would appear if we have just single wavelength illumination. And this center of gravity for this diagram here corresponds to white light. So it's combination of green, blue, and red which results in white light. So if you want to design some standard illumination LEDs for indoor illumination, you want it to be close to white light, and then your spectral irradiance of these LEDs should match after calculating these color coordinates x and y, coordinates which correspond to this central part, and that will be white light. So now if you draw a line from this center of gravity through the color which you determine for your LED until the intersection with this spectrum locus, you will get so-called dominant wavelengths. It is the wavelengths which will be dominant for given color which you determine for your LED. So that's important feature which you need to deal with when you work with LEDs, because it's all made for humans, and our perception of this color of LEDs and is directly related to spectral distribution of its irradiance. So we need to choose those materials and device configurations which will provide spectral irradiance in that shape which will be required for our needs for application of these LEDs, because eventually that's all will be about interaction with humans and their perception of on the screen or just as light in the indoor space.